So here is our third example. In this one, we're not talking about decay anymore. So let's look at it. It says a type of bacteria is growing exponentially with the model y, or f of t, equals 1,000 e to the kt, where t is the time in minutes. How many cells are there initially? There are 1,650 cells after 40 minutes. Find the k value. So let's see what we know. This one is just straight up biology, because some of you on those other examples are going to be like, no, I don't care about geology or paleontology. Okay, got a different ology for you. So this is a biology. So let's go to our equation, and you notice it's that same continuous growth equation. What's the difference? The k value is positive. That's it. It's still f of t equals what? AE to the KT power. So let's go through and think about, what do we know? Well, we know our initial amount. According to the equation, our initial amount is 1,000. 1,000 cells. E is E. K, we don't know K, do we? That's what we're asked to find, right? So then what else do we have? Well, we have T. What is our T? Oh my goodness, my pen's being janky. What happened? Oh, that was scary. Okay. T, according to our problem, is 40 minutes. Be careful to note the units on the problems we worked before. T was time in years. When we did continuous compounding, when we'll do continuous compounding, T is time in years when we're looking at how money grows. But for this one, notice it says T is time in minutes. So T is 40 minutes. What else? We've got A, E, K, T, and then F of T, or Y. All right. And that is what? 1,650. There are 1,650 cells after 40 minutes. So 1,650. Okay, so we have enough to start plugging into our equation. So I'm going to take this, move it up here. Okay, so we're going to say y, or f of t, which is 1,650, equals A, that's 1,000, times e to the k, we don't know, t, and t is 40. So there it is. Our variable is in our exponent spot, so we know at some point the only way to get that out is to do a log, and we will. But we can't rearrange and do a log as long as we've got a multiplying factor out front, or if we had an adding or subtracting thing going on over here. So the first thing we're going to do is divide both sides by 1,000, and that will be our start to isolate our exponential. And when we do that, you could leave it. That actually divides out to a rational number and not an irrational number. So I'm just going to say 1.65 equals e to the 40k. Okay, now we're at the wall. We can't go any further because our variable's in our exponent. So what we can do now is we can rearrange. Now we can logify the situation because e is isolated. So we're going to say the natural log of the value, the exponential value, 1.65, equals the exponent, 40k. And to solve for k, we'll just divide both sides by 40. And k should be positive because this is growth, all right? It's growth. So we're going to have to round, so we'll go ahead and say approximate. And this now, at this point, once you rearrange, y'all, it's just straight up calculator. So go ahead and turn your calculator on, and we'll say the natural log of 1.65 close parentheses, divided by 40. Enter. So yours should look like that. And that's what it is. And we will round that to, let's see, 5 places past the decimal. So K is approximately 0.0125, and then it's 193822, so we'll say 2. So what's the K value for this bacteria on its growth is 0.01252. And then once you know that for that particular type of bacteria, you can predict future growth, all right? So you can press pause here and finish writing this down if you need to. I'm going to go ahead and go on to a second part, comparing this bacteria to a second type of bacteria. All right, so if you need to press pause, go ahead. Otherwise, okay. So this is example 3B. And this is what scientists do sometimes. Suppose a second type of bacteria, and just like right now, when they're doing their studies on COVID-19, frequently they compare those to other known viruses that are similar. So suppose a second type of bacteria is growing at or let's say not at, with the model of, and let's say y equals 50 times e to the 0.0432 t. Okay, so that's the equation that models this second type of bacteria. The question is, how long will it take for these bacteria cells to exceed the first? So you got those original 1,000 cells that were growing with a growth rate of 0.01252. And then you have this second bacteria, and its initial amount was 50. But notice the growth rate. It's a larger number. So that means it's growing faster. So even though the first example is starting out with more, since the second example is growing faster, at some point it's going to overtake and exceed in amount of the first rate. And so that's what we're looking for. How long? So that's a time problem, and we don't know, okay? But we can find out. This one's a little more involved, so hang with me, okay? Let's write the equation of this first type, of the second type. Let's start with the second type. 50 e to the 0.0432 t. We want to know when that's going to exceed the first. Now, exceed is a fancy word, and it just means surpass, or go beyond, or be more than, greater than. I have help over here answering questions since I can't hear you answering. Okay, so it's all right. He's already passed algebra 2, don't worry. So now I want to know when this is going to be bigger than 1,000 e to the 0.0125 t. Mhm. And where did this come from? Oh, we found it in the first part of this problem. All right. So when is this going to be bigger than that? And we're like, we haven't done a problem like this. You're right. We haven't until now. So it's pretty cool because scientists do this. They compare things, they change one thing at a time, they make observations, they collect data, they write it all down. But we can do this problem because look, it only has one variable. All right. So one of the things that can do, we've talked about, is that we can always take a log. We can take a log of both sides. So that's what we're going to do. Only it'll be a natural log, right? Because we're in base E. So let's do that. So I'm going to say the natural log, because I'm going to have to take a log, because the only way that you get the variable out of the exponent spot is to take a log. So I'm going to take the natural log of 50 times e to the 0.0432 t power. Okay. And all that is the argument. Okay. Is greater than the natural log of 1,000 e to the 0.01252 t. Okay. All right. So now look inside the parentheses. What do you have going on? 50e. That's a product. So we can use the product rule and expand this. Right. So I'm going to say the natural log of 50. And remember, the product rule says the log of a product is the same as the sum of the log of the factors. So I'm going to say the ln of 50 plus the ln of e to the 0.0432 t is greater than the natural log of, same thing over here, 1,000 plus the natural log of e to the 0.01252 t. Okay. I use the product property. Now, back when we were looking at properties, we learned about something that looks like this, and it was a special log exponential property, and it said the log in base b of b to the y equals y. If these two things are the same, then the exponent is the value. Right, now, it looks a little different, but I want you to come over here and think about this. Look right here. Natural logs are operating in base E. So if I'm taking the natural log of e to the something, remember what? It's really, there's an e down here. And really, there's an e down here. And so we learned it this way, but it also can be written this way. The natural log, which is in base e, okay, of e to the x. Are you seeing the pattern here? Log base b to the y equals y. Ln base e of e to the x is going to equal what? The exponent. And that's going to help us simplify this one and this one. Okay. All right. This is who we're using right here. So now I'm going to say the ln of 50 plus the natural log base e of e to this is just what? 0.0432 t. How cool is that? That's really cool that happens. And all that is greater than the natural log of 1,000 plus, again, same thing here, log base b of b to the y. What does it equal? 0.01252 t. Shazam! Look at there. We got t is our only variable, and I have one over here and one over here. So now it's kind of, I know we still have that natural log of 50 going on, but it's really kind of procedurally algebra 1. I'm going to get my natural logs on one side, and I'm going to get my t's on the other side, and then I'm going to divide. So I'm going to add and subtract, divide, and then I'll have the time. So let's see. I can subtract this guy over here. So I'm going to say 0.0432t minus 0.01252t. So I'm subtracting this guy from both sides. And all that is greater than the natural log of 1,000 minus the natural log of 50. Okay? Right. So let's subtract these. Handy dandy calculator. 0.0432 minus 0.01252. Oh, come on, pen. And I get 0.03068t on this side is greater than, okay. So now over here, this is subtraction going on. We could condense these if you want. We could say the natural log of 1,000 divided by 50. We could do that, or you can just say the log of 1,000 divided by the log of 50. Either way, we'll get the same answer. So if you want, either way, right? 1,000 divided by 50 is the same as 100 divided by 5, which of course is 20. Okay. Now we can divide both sides by 0.03068. So when I do that, I'm going to divide this side by 0.03068, and I'm going to divide this side by 0.03068. Okay. I knocked over my tea.
Here, take it off your phone.
Here. T is greater than, so let's get our calculator. And we have the natural log of 1,000 over 50, or 100 over 5, or 20. Okay, and then hit enter. Divided by 0.03068. So, you don't round that, right? You just hit divided by, right? Or second answer or whatever. And there it is, 97.644. So T is greater than 97.644, or approximately 98. Now, if we go back and look, what was T talking about in the first example? It was time in minutes, okay? So we will say it will take about 98 minutes for the second bacteria to exceed the first. And for all of you that want to study life science and biology and microbiology and anatomy, there you go. Math supporting you right there where you need it. Okay? Enjoy.